Um, Hello, for those of you who don't know, my name is Adam Usala. I'm going to be talking about a scintillation arc survey with the GBT, or Green Bank Telescope. I did this project with my partner Lily Mathis, who is not here, at Oberlin College. So as I said, this project was done on the Green Bank Telescope. Many of you guys will know of this, probably all of you, but Green Bank is one of Nanograv's sort of two main telescopes, and really great piece of equipment and lots of great data from it. Even though this is older data, we still have some great results from it. So first off, our survey, we wanted to look at pulsars located in Green Bank Telescope's range, obviously, but we exclusively got rid of anything that was in Arecibo's range. We wanted to get things that were sort of unique to Green Bank to utilize it to its fullest extent. So another thing we wanted was that the S400 of all of these pulsars, the flux was at least 40 millijanskis or more. And then we also wanted them to be low dispersion. So in essence, this means we wanted nearby pulsars. We wanted to look at scintillation arcs, or look for scintillation arcs on pulsars that were close to us, because this hadn't really been done in any systematic way. And lastly, I want to note that this was done collaborating with Scott Ransom and Tony Minter at NRAO. They actually went, and I'm assuming stayed up late for many nights in a row taking all of this data, so thank you for not making me do that. And so just to further illustrate the low dispersion, this is a little image I drew up of the location of all of these, oh, lost connection. There we are. The location of all of these pulsars in the galactic plane. So this image is looking down from above. 0, 0 is the galactic center here. It's sort of hard to read the axes, I'm sure. But this is in kiloparsecs, X and Y. And each of those blue dots represents one of our pulsars, with the yellow dot representing the sun in the galactic plane. And the gray ring is sort of the radius of the sun. Just to get a little bit more zoomed in, as you can see, they're all pretty closely clustered. And this is what we wanted. So this is, again, what we meant by low dispersion. So to jump right into it, here's what we found. So we took 18 pulsars, as I mentioned on the last slide. Of these 18 pulsars, 17 of them provided usable data. I think it was 0031. I don't remember plus or minus what off the top of my head. But that one had just really, really low signal to noise, and we really couldn't use the data, and so we threw it out. So of the 17 remaining, though, 15 of them had convincing or clear scintillation arcs. Here's one cute little example here, one of my favorite little spectra, because at first when we looked at this, we saw nothing, and with enough processing, suddenly this very clearly delineated arc popped out. So now I just want to show you a couple of other ones, because as Dan always says, we like to see the pretty pictures. So I'll start off just by talking broadly about these. But one thing I want to note, if you look on the dynamics of almost all of these spectra, you're going to see streakiness to it. There's two reasons really why I didn't process this out. First of all, because time normalization is just, it just messes with the data a little bit, and it just doesn't look quite right. You start to lose a lot of the finer details, which we're increasingly realizing is really important, and that's really what's giving rise to some of this structure. And also because it just resulted in a totally sort of unrealistic looking dynamic that was sort of fuzzy. So the first spectra here on the left is one of my personal favorites. It shows a lot of this patchiness that we've seen in a number of pulsars before. And this patchiness, I believe, was tracked in a paper by Dan and a number of other people. You can watch these patches move across the arcs, and Dan, you're shaking your head. Well, yeah, it was a different pulsar, but these features have been tracked, and you can see that this is appears to be resulting from just random clumps of material in the ISM as the pulsar is moving. This pulsar, as Dan noted, has not been looked at, but has the potential to be. On the right, some really interesting inverted arclets, which we've seen on a lot of other pulsars. Next one here, if you look, I don't know how well it's going to show up on the screen. On the computer, it's a lot more clear. But on the left side, you see a couple of, you see the beginnings of two very nice little parabolas coming out, one wider one and then one narrower one in the center coming out of the noise there. I also want to draw attention to, on the dynamics here, One of them, you'll see a field of just a couple of scintillation arcs, just large scintillation arcs on the left, and then on the right, you see really small ones. This is something that you will probably, scintils, yeah, scintils, that you'll probably be seeing or hearing a lot more about from Dan and hopefully myself and other students from Oberlin, because we're really noticing that what the field of view that we're looking at in the dynamic spectra is really important to what we see in the secondary spectrum, specifically the ratio of how large our scintils are compared to our frequency resolution. And one last one that I think was very pretty. You see on the right side here a very clear outer arc with a filled-in inner arc, and this is something that's been looked at by, this connection is very loose, that's been looked at by a number of people, but a lot of these phenomena do not have clear answers, so there's a lot of things to look at here and try to understand. So this, some of you may be sitting here thinking that you've looked at 100,000 arcs or 100,000 secondary spectra, and you do not see arcs in almost every one of them. And I think one of the keys to why we saw so many is because we observed at multiple frequencies, namely 340 and 825 megahertz. And this really allowed us to see sort of this, not all of these pulsars showed scintillation arcs. If we just looked at 340 megahertz, we might have seen only 8 or something like that. So I just want to show you a couple examples of how multiple frequencies really helped us here. So this first one here, I particularly like because this really illustrates, also Barney mentioned 2 minutes? Okay, this also illustrates something that Barney mentioned with the lack of frequency resolution. On the first spectra, we really couldn't see everything we wanted to, but by going to a higher frequency, we're able to see the structure, which I'm going to zoom in on, namely this little split in the middle here, which we firmly believe is the beginnings of a scintillation arc forming. Now, I'm going to keep losing this, it seems. I'm going to skip through this next one because I'm running out of time, but if you look here, we have one spectra here that doesn't appear to have an arc, and then suddenly, when we look at the higher frequency, we see an arc appear. So how common are these arcs? Why don't we see 100 of them, or why do we always seem to see one? The real answer is we don't know yet, but it's clear that there is no real limit to how many we can see. As we've seen in this data from a different survey, we sometimes see as many as 4, probably even 5 arcs that appear, and this is really exciting because we don't understand it. So what do they tell us? First of all, scintillation arcs are visible on almost every line of sight. This seems to give a lot of evidence toward this discrete sheet model of material in the ISM, and we see this evidence for it on almost every single pulsar. But this also provides a new way to look at scattering in the ISM as scattering through these sheets. So this is really, really exciting. I'm going to go quickly through this because I'm low on time, but this is sort of extreme examples of these 2 types of scattering that I'm talking about. So this, on the left, you see sort of scattering in an ordered way through a sheet because you have a one-to-one relation between the angle of scattering and the curvature of the arc. And so on the right, you have sort of a random scattering that would result in sort of a Gaussian halo, which we see on a lot of spectra. You look down near the origin and you have this sort of Gaussian fall off. So possible explanations, again, we don't really have any. There have been some proposals about them. For example, Jim Cordes, Roger Ramani, and Roger Blandford in 1987 proposed this idea of supernova blast waves giving rise to something to these sort of sheets, but again, not quite sure. And so, last slide here. Going forward, we really want to focus on using this as a tool to probe the interstellar medium through the secondary spectrum. And also, I'm going to be doing a year-long honors project specifically looking at the distribution of material between these sheets and this extended medium in the interstellar medium. And so that's going to be really exciting. I think we're starting to get a lot of insight into how we can do this in a more rigorous way. And if it wasn't already clear that I'm a student of Dan because of all these questions that I raised, there's so many questions, and it really is exciting being part of this. And so I hope that we have lots more to talk about going forward. Thank you.
Great talk. Any questions?
I really don't understand the streakiness in the dynamic spectra. The GBT gain calibration is stable over
So
timescale of these observations?
yeah, so this comes from,
Just go back to
yeah, let me.
picture that shows it.
That would be earlier on. Yeah, here. Oh, and naturally it's gone. Yeah, so this is partially due to, yeah, so these are just the data is taken in 10-second time integrations, I believe. And here what we're seeing is just that the number of pulses coming in that given integration can vary slightly. So, so that all that is just, you know, 7 pulses versus 5 pulses in a certain integral.
Must be pulse-to-pulse variability.
Yeah.
That would be much more regular if it was
Yeah.
But then you should be, there's really no reason not to divide that out. You just take an average.
Yeah, but the reason I don't want to, because at least our algorithm for getting rid of it was it just smoothed it to sort of an unnatural looking, like it looked like it was touched up a lot, and I think I enjoy looking at this as sort of as natural as I can make it without RFI just blotting it out completely.
I would just add a clarification. I actually agree with Martin on this. There's another algorithm that that we haven't employed here that works, that I think works just fine for taking this out, because actually, I mean, leaving it in also has its own problems, right? Because it's
Right.
it's a window function.
And I think it's that cloud and power kind of that's independent
Yeah.
of
Mhm.
frequency that is coming from that straightness.
Mhm.
No, I think
I think this will not affect the secondary spectrum in any significant way because this is very high frequency.
No, it does.
Yeah.
I know
I think Matthew's right. It's basically his whole bottom line.
Yeah.
Mhm.
You
Right.
can see the like individual, the patches there.
So the question on the way back, so you have high incidence of gravel,
Yeah.
and what's the incidence of multiple gravel?
We have not really we didn't really specify the number of arcs in this survey, but I would say in this sample, and this is a guess, but a good guess, there was probably 4 to 5 that showed multiple arcs. And again, these are close to us, so if we're trying to imagine these sheets somewhere scattered in the interstellar medium, it would be surprising to see as many as we see on something like 1133 plus 16. But there is a non-negligible percentage.
Picture, right. The picture of this is lots of sheets.
Yeah.
All of them that are
Yeah.
not exactly aligned don't count.
Mhm.
But how many are close enough aligned to do something,
Mhm.
maybe a minimal thing? And actually, when you count 4, do you count this one? I mean, I think so.
So yes.
In your guess, you would count this one as one with multiple arcs.
This one,
Yeah.
no, I would be skeptical on this. This is sort of where I say 4 to 5.
I have no choice. This is
I would
multiple
count
arcs.
Yeah.
I would count it as
Okay.
multiple.
Yeah.
I mean, because of seeing that, yeah.
Well, I think this is probably a discussion should
Mhm.
go on
Yeah,
over
it's fine.
coffee. So
Absolutely,
let's
yeah.
take